那我们开始今天的 Global Talk。今天很高兴邀请到宾州州立大学李文清教授。那李老师之前是这边理论中心的主任，然后当了6年。那很高兴我们今天有机会请李老师来给这场演讲。那今天的 title 是Novel Applications of Ramanujan conjecture。那我们再次欢迎李老师。
很荣幸今天有这个机会，也很高兴今天有这个机会，然后再度回到清华大学。回到清华大学，给我感觉很像回家一样，看到很多老朋友，觉得很亲切。So I will switch to English. So today I'll be talking about the novel applications of the Ramanujan conjecture. So Ramanujan conjecture is a very deep and important conjecture in number theory. So it is actually very surprising that one can find applications in computer science. So I will begin by explaining the Ramanujan conjecture, then I will talk about the applications. So Ramanujan conjecture originally concerns the estimate of Fourier coefficients of modular forms. So I will start by talking about modular forms. So we know that the group SL2Z acts on the Poincare plane by fractional linear transformations. So if one let's consider not only the action of SL2Z, but also the finite index congruent subgroup gamma, and look at its action on the alpha plane. So we are interested in the functions, holomorphic functions, on the alpha plane, which has a lot of symmetry with respect to this action of gamma. So a priori, one would be interested in the functions which are invariant under the action of gamma. If we also require the function to be holomorphic, then there's only one kind, and they're constant functions. So that's not too interesting. So if we go beyond that, so the next one is that we assume there's a relationship that f as the image of gamma and z and f of z that differ by this factor cd plus d to the k, where the cd comes from the second row of this matrix gamma. So k here is fixed throughout for this form f. K here is positive integer, is called the weight of f. So this relation comes from originally comes from case k equals 2. That comes from the that means that f z dz gives you invariant differential on the alpha plane of gamma. So this is a generalization of a holomorphic differential. So in addition to this condition, another condition is that we look at the orbit of this action, so alpha plane modeled by gamma, and we can compactify this quotient by adding finite many points called a cusp. Okay. We also require this function to be holomorphic at the cusp. And in particular, if this function also vanishes at all the cusps, we call this function a cusp form. So cusp form is what we are interested in. So let's consider the basic group, just SL2Z itself, and think about the cusp forms for SL2Z, and we begin from the low weight, k equal to 1, and all the way going up. Okay. And the first weight that SL2Z has a cusp form is when k is equal to 12. And that function it's a famous function. It's called a discriminant. But in a sense, it's probably one of the most important cusp forms for the when one considers modular forms for the congruent subgroup. So it's called a discriminant function because it gives you a discriminant of this elliptic curve. Let's not talk about that, but let's go back and look at this expression. So SL2Z contains all the translations. Translations corresponds to the matrices 1, B, 0, 1. So when gamma is a translation, C is 0, D is 1, that means that our function will be invariant under translation. Okay, by 1, that means that the function has a Fourier extension. So we can express this delta in a Fourier extension in the powers of e to the 2 pi I t. Because we required it to be homomorphic at the cusp and vanishing at the cusp, so this Fourier extension starts from n equal to 1 and up. And tau of n is the Fourier coefficient. So this function back in the 19th century, it was proved by name escapes me. So it's known that this function has this expression as infinite product of a function of Q. So if you do not know this function before, you may take this as a definition. When you extend this, and you can write this as a series in powers of Q, with coefficient tau n. So here you see that the tau n is integer from this extension. So Ramanujan computed this Fourier coefficients for about 30 of them, and from this from the data, he made the following amazing conjecture about this Fourier coefficients. Okay. So he did this in 1916. So the first property is that the tau is multiplicative. That means that if the indices m and n are co-prime, then tau m equals tau m times tau n. So the first property tells us that to know all the Fourier coefficients, it suffices to know that for all the prime powers. Then you can put it together using this relation. So now let's look at what happens to the prime powers. Then he conjectures that if we fix the prime p and look at the coefficients at p to the n plus 1, p to the n, and p to the n minus 1, and he says that they satisfy some recursive relation which holds for all powers of p. So if we start from tau of 1, which is equal to 1 from that extension, so when you take n equal to 1, tau of 1 is equal to 1. So if we know what is tau p, then we will know tau p squared. Then if you know tau p squared, you will know tau p cubed, and so on. So you keep on building up. So from these two expressions, we know that if we know all the values of tau p, then we will know all the Fourier coefficients. So the third property talks about the size of the Fourier coefficient. It says that a tau of p has absolute value bounded by twice of p to the 11 over 2. So notice that this 11 is the weight k, which is 12, minus 1. So one can reorganize the first two properties in terms of the L function associated to this modular form. Mainly, one can take the Fourier coefficients, tau n multiplied by n to the minus s, and summing over all the positive integers. And so this is a Dirichlet series associated to the function delta. It converges for the real part of s for sufficiently large. So there's no question about that. So this is a nice holomorphic function on some right half plane. So the first two properties about the behavior of tau can be summarized by saying that this infinite sum can be expressed as infinite product over prime p, and its factors 1 over 1 minus tau p, p to the minus s, plus p to the 11 times p to the minus 2s. So the coefficients there comes from the coefficients of the recursive relation. So this reformulation actually was already noticed by Ramanujan himself. So the way to write the L function associated with delta as infinite product over prime p in modern language is saying that this delta is an eigenfunction of Hecker operator at p with eigenvalue tau p for each prime p. So the original conjecture, the first and second statement of Ramanujan's conjecture was proved by Mordell in 1917. But this expression here, the L function can be written as product over primes, is very intriguing. Okay? So Hecker looked at this statement, and he extended this phenomenon to all the modular forms. Namely, if you fix the weight and you have a finite dimensional vector space, then you can find a basis or form that whose L functions then can be written as a infinite product in this way. So the third statement of Ramanujan's conjecture is on the size of tau t, absolute value bounded by 2 p to the 11 over 2. So that can also be restated in the following. So let's take the denominator here of this L function. Okay. So regard this as a polynomial, quadratic polynomial p to the minus s. Okay. So then I can factor that the product of two linear factors in p to the minus s. So I have this constant alpha t and the beta b in front. And so you think that you have a polynomial degree 2, and here we factored it to give a bound on this tau t. The way we said that means that the discriminant of this quadratic equation, this polynomial, is less than or equal to 0. So that's equivalent to saying that alpha t and the beta b should have the same absolute value. In this case, in the square root of p to the 11. Okay. So this expression here is called a Ramanujan conjecture. And for the delta function, it was proved by Deligny. And when he proved this, he also did it for test forms in general. Okay. So he did this around 1973. It's a part of the work for his Fields Medal. Okay. And this statement for the case form of weight 2 was given by Eichel and Shmura earlier. And after Deligny's work, and Deligny's fair also settled the case with 1. So for all the homomorphic modular forms, the Ramanujan conjecture is known. And then Maynard can reinterpret the modular forms in terms of representations of GO2 over Q. So when you see the modular forms from the viewpoint of representation, then one can also generalize the Ramanujan conjecture. So we can generalize it to a very general case. So the group, instead of GO2 over Q before, we can replace it by any reductive group defined over either a finite extension of Q, which is called a number field, or finite extension of the polynomial of the field of rational functions over a finite field. That's called a function field. So in this case, let's take cuspidal homomorphically reducible unitary representation of this group over this field K. So this kind of representation is a global object. This global object is a tensor product of local representation. And we say that at its pi satisfies the Ramanujan conjecture. That means that its local representation is so-called a tempered. What this means is that if you look at the matrix coefficients of this representation, okay, so the matrix coefficients are the functions of the local points of this group. Okay. And to say that its representation is tempered, that means that all the coefficients should be lying in L2 plus epsilon space for all epsilon possible, just slightly weaker than L2. And it is known that the Ramanujan conjecture does not hold for all. So there are counterexamples that for which we can find such kind of representation for which Ramanujan conjecture does not hold. So now people believe that it should hold for the case that the representation is called a generic. Okay, so this is a very, very general statement. Okay, maybe a little fancy. So let me give you some examples to see that more down-to-earth situation. Okay. So if I take the group to be G defined over Q, okay. So if I take the representations as this, then it comes from two sources. One is from the holomorphic cusp form. The other one is from the real analytic mass cusp form. Okay. So if they're coming from holomorphic cusp form, then when I look at the local components, because it's over Q, so over the place at infinity, this because the form is holomorphic, that means representation is either discrete series or limit of discrete series, so it's always tempered. So there's no problem about component at infinity. And the classical statement about the Ramanujan conjecture concerns the temperedness of the pi at the prime p, when prime p varies. Now, if this representation corresponds to a mass form, so let's see what does it mean by saying that a corresponding representation of infinity should be tempered. Okay, so being a mass form means that this form itself is an eigenfunction of the Laplacian and with some eigenvalue. So this part is the property of the form. And to say that representation is tempered is the same as saying that its eigenvalue should be at least 1/4. Okay, so this is the strange connection between representation property and the eigenvalue of Laplacian. Okay. And this temperedness conjecture part here agrees with the 1/4 conjecture for the congruent subgroup. Okay. So
what is V in the general case?
Huh?
What is V in the general?
Okay, V is for the places. So for the field, so if you think the field K is Q, then this V, one is the Archimedean variation, all the others are the p-adic variation, one for each prime. So this is a number theorist way to see things. We think of this number field as a global object, and the points on that are the variations. So for the mass form, actually none of this is known. There's no single example for which that one knows that a pi infinity is tempered. So if the group is a GON, okay, the GON we have an L function associated with pi, and it's a product over, say, take a K to be Q, that'd be product over prime P. So it's 1 over the denominator will be a polynomial in p to the minus s of degree at most n. Okay. If the representation, say pi p, is unramified, then it has degree n. And in general, if we are given such kind of representation, only finite many local representations not ramified. So which means that for almost all places it's unramified. So we will have a degree n denominator in the powers of p to the minus s. So to say such unramified representation is tempered means that I look at the roots of this degree n polynomial, they should all have the same absolute value. So as you can see here, Ramanujan conjecture has some flavor of the Riemann hypothesis by saying that the roots all have the same absolute value. And indeed, this conjecture has a lot to do with the Riemann hypothesis. So the Ramanujan conjecture is largely open. So it's a proof for some special cases, which I'm going to discuss. So then you first say that how the special cases were proved. So the standard way to prove the Ramanujan conjecture for a representation is to find another representation. Find the representation of a Galois group corresponds to pi as predicted by Langlands. So you have to prove some part of the Langlands program with respect to this representation. Okay. So once you have the corresponding Galois representations, then the Ramanujan conjecture would follow from the Riemann hypothesis for the underlying geometric objects on which this Galois group is realized. Okay. This is how Deligne proved the Ramanujan conjecture for the delta function And this is how the other Ramanujan conjectures were proved. Okay. It's the same philosophy. So that's the main way, and this is a very hard work. Okay. And the second way is by Langland's temporality. This is sort of a piggy bank of the first result. So if I have a group, I have a representation, I want to prove that this particular representation, well, satisfies the Ramanujan conjecture. So my way is that to find another group, second group, for which I know that the Ramanujan conjecture holds, okay? And then I try to establish a correspondence from the representation of the first group to the representation of the second group, which respects the Heck operators. Okay? This is called the Langland's temporality. If you can establish that, then you can piggy bank on the fact that you already know what that the Ramanujan conjecture holds for the second one, therefore it also holds for the first one. So let me review the known cases. Okay. So the first is the case that we look at a finite extension of the field of rational functions. Okay. So this field has finite characteristics. Okay. So the first case is true for GLN. Okay. So n equals 2 is what proved by Greenfeld, and in general proved by Laforgue. So they are all fields medalists, especially Laforgue received his field medal because of this work. So their method is to establish the Galois representation. Then the second is that I take G to be the multiplicity group of a central simple division algebra of dimension n squared. Okay. So in this case, this is using the second method, temporality, because the second group is the GLN, and we know that the Ramanujan conjecture holds for GLN, and then we establish correspondence between the representations of two groups. And this is called the Jacquet-Langlands correspondence. And n equal to 2 was done by Jacquet, Langlands, and in general was done by Baudelaire and Laroche, and this was done in 2016. It was very recent. And for such kind of this H cross, actually, if we do not require it to hold for all the generic Cuspidal unitary representations, and if we accept that back in 1993, Lomond, Rappaport, and Stuhler already proved the Ramanujan conjecture, but only for the representations with extra conditions, namely you want it to be Steinberg at a certain place, which is where the algebra is not ratified. Okay. So they established the Galois representation. And then in 2009, Lomeli established the conjecture for the orthogonal group, SO, and the symplectic group. Okay. So he uses the temporality. Now, over number field, what we know is much less. Okay. So the first is the case G equals GO2 over the field Q that we already discussed for the linear higher weight and Schmuller weight 2 and the linear weight 1. Okay. And the second is the GO2 over totally real fields that's by Brzezinski, Labette, and Glaciers. And so this is established the Galois representations. Then the second is using the Jacquet-Langlands correspondence, taking H to be the quaternion algebra of a totally real field, but we want it to be ratified at all the Archimedean places because what we know before is only for the holomorphic case. And more recently, one has results for GLN over the number field with the complex multiplication. But not for all the general situation we said before, but with some extra condition on the representation pi. So this started by the work of Cosell and then extended by Shin. By extension, that means that you gradually reduce the condition on pi. And what I showed here, the algebraic regular and conjugate self-zero is the simplest condition. And then it's also true for certain unitary group representations by Kozel, Harris Taylor, Shin, and Ebra Pazanshevsky. I will talk about their work later. Now, in general, we said that for mass forms that even for GL2 over Q, there's no example for which we know the Ramanujan conjecture holds. But in general, one can give some kind of bounds on the absolute value of alpha p, beta p, like that. Okay. So the best bound was given by Rudnick and Sarna. Okay. So they have a bound for general n, but when n is small, like 2, 3, and 4, Blomer and Brunwick improve their bounds. Okay. So these are all the works in the annals and so on. Okay. So these are the current status of this conjecture. So next, I'll go to the application. So first, I'll go back to talk about give a little bit background about the spectral theory of regular graphs. So let's consider a finite connected undirected graph. Okay. Let's assume that it's Q plus 1 regular. That means that each vertex has Q plus 1 neighbors. Okay. So to describe this graph is the same as describing the adjacency matrix, whose rows and the columns are parameterized by the vertices, and the ij entry tells you how many edges from vertex I to vertex j. Okay. And the adjacency matrix can also be viewed as an operator of the L2 functions on the vertices of the graph. So send the function f to another function whose value at the vertex z is the average over the neighbors. Okay. So since this adjacent matrix is a real symmetric matrix, so we know that its eigenvalues are real, we can arrange it from large to small. And since this graph is a Q plus 1 regular, it's easy to show that eigenvalues sit between Q plus 1 and the minus of Q plus 1. And the Q plus 1 is an eigenvalue because constant function, well, is an eigenvector. Okay. And because we assume the graph is connected, so we know that the second eigenvalue will be less than Q plus 1. So the gap between the first and the second eigenvalue is called the spectral gap. So spectral gap gives important information about the graph, which we're going to discuss. So let me also say that if the smallest eigenvalue is equal to minus Q plus 1, and that's the same as saying that the graph is bipartite. So we know very well the largest eigenvalue, which is Q plus 1, and whether this minus of Q plus 1 is eigenvalue. So this plus minus Q plus 1 are called the trivial eigenvalues. All the rest are the non-trivial eigenvalues. So now let me say a few words about the spectral gap. So we talk about the graph because we have in mind as application, we want to think of this graph represents a communication network. So when you use this X as a communication network, its efficiency is measured by something called the expanding constant. And to compute the expanding constant is very time consuming. And fortunately, Penner and Milman discovered that there's a way to estimate this expanding constant. You see that it's bounded from below and above by functions in the spectral gap, the gap between lambda 1 and the lambda 2. So it shows that the larger the spectral gap and the larger the expanding constant, which means that the more efficient this communication network is. So in computer science, one is interested in finding the regular graphs, which are very good when you use them as communication network, with large expanding constant, which means with large spectral gap. So the question is that, well, how large can this spectral gap be? That means that we want to understand the distribution of the non-trivial eigenvalues. that's the spectral theory for the regular graphs. So let's assume that we have a family of a Q+1 regular graphs with size going to infinity. So it's a very well-known theorem of Alokotana, which says that if we consider the largest non-trivial eigenvalue of this graph, this is the lambda 2 of this graph, and as the size of the graph goes to infinity, the lim-inf of lambda 2 is the least pi through q. Okay, q is here is the valency minus 1. And it's natural to ask the symmetric statement. Take the smallest non-trivial eigenvalue and take a lim sup of that to see whether it's less than or equal to minus 2 q. Okay. So unlike the largest non-trivial eigenvalue, the second inequality does not hold unconditionally, but it holds under very simple, mild assumption. For instance, if the graph contains few short cycles of odd length, or the length of the shortest odd cycle will go to infinity with the size of the graph. Okay. In that case, that we will have the second inequality. So the meaning of these two numbers, 2 root q and minus 2 root q, is that if we consider the closed interval for minus 2 root q to 2 root q, so this interval is the spectrum of the Q+1 regular tree. Okay. And you know that Q+1 regular tree is simply connected, so it is the universal cover of any Q+1 regular graph. So then the meaning of the earlier statement is that if I take a very large Q+1 regular graph, then I look at its largest non-trivial eigenvalue and the smallest non-trivial eigenvalue, it's very likely that they will go outside of this interval. So when that thing does not happen, it means that this graph is very special, and that graph is called a Ramanujan graph. Okay. So, so graph is a Q+1 regular graph is Ramanujan, if and only if all the non-trivial eigenvalues satisfy the bound that's the value of lambda bounded by 2 root q. Okay. And another way to see this is to look at the quadratic equation 1 minus lambda u plus qu squared. So this bound is equivalent to saying that all the roots of this quadratic polynomial have the same absolute value. In this case, it's q to the minus half. So when you see this, that this has some kind of flavor, just like what we saw for Ramanujan conjectures. So for the way the Ramanujan graph is defined, we know that the Ramanujan graph is spectrally extremal. Okay. And so they can, when they are used as a communication network, they are excellent. So let me give you some examples of Ramanujan graph. So if you get nothing, I want you to take this home. So this is an object which everybody knows very well. What is that? A soccer. Okay. So if you look at a soccer, so you think of this is a graph which is drawn on the surface of a sphere, and each vertex has 3 neighbors. So this is a 3 regular graph. It has 60 vertices. So if we strategically add one more line so that each vertex becomes 4 regular, and put a carbon at each vertex, so this is the famous C60 buckyball. This is the most studied fullerene in chemistry. And there's another way to see this is that this 60 vertices on this graph actually represents the elements of a PSO2 over a field of 5 elements. Okay, so there's a nice structure for this Ramanujan graph. So you see that on this surface we have glue together the bunch of hexagons and the pentagons. If we change the location of the pentagons, we can squeeze in more vertices, like you have C80 in this case, and this one you have C84. Okay. So we have seen 3 examples of Ramanujan graphs, which you can draw on the surface of a sphere or its planar. Okay. And it's a theorem that there are only finite many Ramanujan graphs of this kind. Okay. So then next, let's go to the higher dimensional analog. So in this case, I will consider the field which we call the non-Archimedean local field, say like field of p-adic numbers, QP, or the field of Lorentz series over finite field at Q. Okay. So we assume that this field has Q elements in its residue field. And the Burhattis building for this group, PGLN over F, okay, has a vertex set. Is this PGLN F marked out by its maximum compact subgroup. So each vertex can also be viewed as equivalence class of rank N lattice over F. Okay. So there's a way to define how the 2 lattices are adjacent, etc. So once you know the adjacency, then you have, if you have 3 mutually adjacent vertices, then you have a triangle, then you add in, do you have a face? If you have 4 mutually adjacent ones, then you have a tetrahedron, etc. You keep on growing. So then you will find out that this building actually is n-1 dimensional simplicial complex. And it is contractible. And because the vertices can be written in this way, the group PGLNF acts on the left-hand side. It preserves all the simplicities. Now, because this building itself is contractible, so it serves as a universal cover of all finite quotients. When n is equal to 2, this building is the Q+1 regular infinite tree. Okay. So this is the universal cover of the Q+1 regular graph that we talked about before. So in general, for PGLNF here, the vertices are partitioned into n types. Okay? You can color them with n colors. We can label them by integers mod n. So the vertices of the same type are not adjacent to each other. So the adjacent ones are the cross with different types. So if you just look at the vertices and the edges, okay, this structure is called the one skeleton of this building. It is an n-part graph. So in this case, there are n-1 operators acting on the L2 functions on the vertices of the building. Okay. Because we have partitioned the vertices into different sets. For instance, the I adjacency operator takes a function its value at vertex. It's summing over the neighbors, but originally for the graph, we're summing over all the neighbors. Now we have final structure. We do not sum over all the neighbors, but we only sum over the neighbors whose type is I more than type of the starting vertex. Okay. So this is the final partition of the adjacency relations. So this n-1 operators, they can be simultaneously diagonalized and generate the hectaedron for PGLNF. And the spectrum of this operator on the building is known. McDonald obtained that. So I showed that the analog of Fontana theorem holds. That means that if you have an infinite family of finite quotients of the building with the size going to infinity, okay, now we have n-1 operators. So for each operator, you look at its eigenvalues on the finite quotient. In this case, they are complex numbers now. Okay. So you put together all the eigenvalues you vary the quotients. But you fix the operator. Okay. You vary the quotients. You collect all the eigenvalues. If you take the closure of that should contain the spectrum of the corresponding operator on the universal cover. Okay. So this is like before that they want to go outside of the interval. Now they want to go outside of the spectrum of the universal cover. So if we have a finite quotient, if all the non-trivial eigenvalues will stay within the spectrum of the universal cover, we call this finite quotient the Ramanujan complex. Okay. And an equivalent statement of this is that we can organize this n-1 Peck operators and define suitably normalize them, define a polynomial of degree n. So this is the matrix. Then we take determinant. Then I look at the non-trivial zeros of this polynomial, and they all have the same absolute eigenvalue. Okay. This is the meaning of this finite quotient to be Ramanujan complex. So in real application, it would be very time-consuming if you are given a regular graph, you compute its eigenvalue, then you check whether it's Ramanujan. It would be more desirable if we can construct Ramanujan graphs and then use it so that we are guaranteed that the graph is already known to be Ramanujan. Okay. So the first construction was given by Lebowski, Phillips, and Song, and independently by Margulis in 1988. Okay. So they did it for the group of p-adic field where p is an odd prime, okay, and the n is equal to 2. So they take a Hamiltonian quaternion algebra over Q. This is the one we all learned in the algebra course, obtaining Q joining the I and the J, I squared and J squared equals -1, and IJ anti-commute. So this is dimension 4 algebra over Q. And this Hamiltonian quaternion verifies only at 2 and infinity. And the group here we take is that we take the multiplicity group marked out by the center. And because our prime P is odd, so Hamiltonian quaternion algebra is unverified there. So if we look at the QP point of the group marked out by its maximum compact, it's the same as the PGL2 QP marked PGL2 finds out that it's maximum compact. That's precisely the beauty. So in this case, we take a set of p plus 1 integral quaternions with norm p, which represents the Heck operator p, and it's a symmetric Mach center. Okay. So let me just give you an example. If p's come to 1 Mach 4, you choose this Fp, which will be the integral linear combinations of 1, I, j, and ij. Okay? Because p's come to 1 Mach 4, and we know that its norm, which is the sum of 4 squares, is equal to p comes to 1 Mach 4. So exactly 1 is odd and 3 is even. So we require that A is odd and we require to be positive, and the BCD is even. So this is the set. This is the set that the p plus 1 element which have the desired property. So, and the Lebowski and Salmak show that this set generates a free group in the p-adic points of this group D. Okay. And more importantly, okay, we said that the tree here is a coset space. This PGL2QP marked out by its maximum compact subgroup. Normally, when you want to represent a coset space, you only get a set. But in this particular case, you find a representative which form a group. And that group is a group we call the lambda P. It's a group generated by SP. And so they show that if we consider another prime, which is large enough, okay, and we now fully take the advantage of that the points in lambda p have coordinates, or integral coordinates in z, so I can do this modulo p, modulo q, sorry, and I pick up the elements which I count to 1 modulo q. So this is a congruent subgroup. And this congruent subgroup has finite index in lambda p. Or so when you take the tree model out by this congruent subgroup, you get a finite p plus 1 regular graph. And this graph is Ramanujan. Okay. So you can vary this second prime q. So you have infinite many congruent subgroups you can mark out, and you get an infinite family of Ramanujan graphs. So it's a similar construction. You can change your quaternion algebra. You can change this group, discrete congruent subgroup you mark out, or you can even change the field. Same idea. You can get lots of Ramanujan graphs. And by the way, such kind of Ramanujan graphs are being used, really used by some companies. So all the Ramanujan graphs were constructed above, so by number theory using the Ramanujan conjecture or transforms. They all have the valency, which is the prime power plus 1. So it has long been a question, what happens if I have a valency which is not of the form prime power plus 1? Are there infinite family of Ramanujan graphs? Okay. So this was answered by computer scientists Marcus Spillman and Srivastava in 2015. So they proved the existence of infinite family of the q plus 1 regular Ramanujan graphs, but they have to require their graph to be bipartite, okay, for any q. It doesn't have to be prime power. So it's still open question that if I cross out the word bipartite, whether there are infinite many such families of Ramanujan graphs. So then the same idea by the Lubavitch-Pirisana can be extended to construct the Ramanujan complexes. Okay. So in this case, the field is no longer QP, but it's the field of Lorentz series. Okay. And we can find the infinite many discrete Poisson-free co-complex groups so that we can mark out to get finite Ramanujan complexes. Okay. So this was done by various set of people using different kinds of situations where the Ramanujan conjecture was known to hold. Where should I see my hope? Okay. Let me just quickly say how this was done. It's very similar to what we saw before. Okay. So the idea is that we think of this field as the completion of the field of rational functions at some degree 1 place, which is not that indicated. Then we take central simple division algebra dimension n squared, which is unverified at the B and totally verified at infinity. And the group is the multiplicity group marked out by the center. Okay. And because of the way we choose our verification, so we know that the local point of the B marked out by the maximum compact gives you the building. And just like before, what we saw for the case of graphs, now we want to choose a bunch of the congruent subgroups, and they come from the global rational points. So the way we say it this way is that we take an open compact subgroup or the product of maximum compact over all the places outside infinity and the B. Then we take the global rational points, which we put no conditions at the B and infinity, and then other places are coming from our prescribed conditions. Okay. So in this way, we pick up points which are integral outside of B and infinity. And then when we take our building marked out by such a congruent subgroup, the advantage is that because of the way we choose our group, it can be viewed globally as a quotient of our delta points. So this allows us to see the functions from the vertices of the finite quotient as functions, or automorphic functions of a group. So then we just have to choose this K very carefully, such that the functions on this finite quotient are orthogonal to the constant functions as well as the twist by roots of unity. They can be interpreted as generic cuspidal automorphic forms. Then we are done. So I would like to end by talking about some other applications, which is also, I think, is very striking. Okay. So let's go back to the case of quaternion algebra. That's the Bartley-Figure-Stomach case that we solved. Okay. So when it's over Q, it has one place, namely the place at infinity, which is very different from the place at P. Okay. So I look at the quaternion algebra, look at all the real points. Okay. All the real points with A, B, C, D here in R, we can, well, send it to the 2x2 matrices with complex entries, with A plus BI and its conjugate here, and C plus BI and the minus of its conjugate on the cross anti-diagonal thing. So that the norm on the left-hand side becomes the determinant of the matrix on the right-hand side. So that the norm 1 elements on the real quaternion are sent to the group we call SU2 on the right-hand side. The SU2 projects onto SO3, and SO3 acts on the sphere to speed. So we remember that we have this set SP, which was used to build this group lambda P, which represents the vertices of the C and P. Now the same, because those points have coordinates which are integral, so you can view them as real points. And because we mark out by the center, so I can mark out, I can normalize it by namely divide all the coordinates by square root of P such that I end up with elements which have norm 1. Okay. So then they generate a normalized group, lambda P, which I send it to the right-hand side, which lies in PU2. And the PU2 itself, you look at the image in SO3, it has dense image in SO3. Okay. So we managed to put a lambda P as a dense group in SO3. Then SO3 acts on the sphere S2. So they take any points on S2, then we just move around by the image of lambda P in SO3. So they show that this image is uniformly distributed on the sphere. Doesn't matter which point on the sphere you choose. You look at orbit. That orbit is uniformly distributed. So this fact can be used to approximate the integrals on the sphere. So you can just estimate them on the images of lambda P. Okay. And same, all the lattices, all the discrete subgroup we have chosen, we can also normalize it and look at the action. They have the same property. They are all uniformly distributed. So this result was generalized by Cosell from S2 to S2n minus 1 using the unitary group. So then I want to talk about another application, which is in quantum computation. Okay. So in quantum computation with n qubits, so the quantum bits. Okay. In this case, the global logic gate is P is UN plus 1 mod out to the center. Okay. And in quantum computation, the big goal is to find a symmetric subset. Okay, with the following properties. So the elements in the subset should be uniformly distributed, and when you add more and more points generated by the product from the elements of a subset. The whole thing is also uniformly distributed, as uniform as can be. Okay. And second is that if you consider all the products together, they are dense. And in any, if I choose any point in the group, okay, so it may not lie in this image of generated by the set S, but because this union is dense, so I take any epsilon neighborhood of this point A, it should contain some points. So there should be an efficient algorithm to find that point, which is in some power of S, okay, which is within the epsilon neighborhood of A, and hopefully we can find this R, which is the smallest one, and there's a good way to express this element as a product of R elements in S. So all this is what we have in mind is that in quantum computing, when we use quantum computers, because quantum computer is very unstable, each time when we are doing the computation, we should be constantly correcting the mistakes. So the points generated by the powers of S, say like here, up to R power, you can think of that as the quantum code. So you express your information inside this quantum code. But because the computer is unstable, and when you send out the code, the computation will give you anything, any point in the group. Okay. So that's what it's called the A. So then when you receive the A, you want to correct it to find the code which is the closest to A. This is our A prime. And you want to decode it. Okay. This tells you efficient way to do it. So it turns out that if we fix the size of the set F, okay, we want to think that how uniformly distributed it is on the surface. So, what do I do? So there's a measurement. Okay. So if you take the Haar measure, so if the whole group has a Haar measure 1, okay, you take this set S, you look at the epsilon neighborhood, okay, there was some overlapping. You look at the volume covered by the epsilon neighborhood of points inside S, okay. So its lower bound is 1, which is the whole thing, minus, okay, this fixed proportion. So fixed proportion has some constant depending only on epsilon, and the size of S squared, the denominator. So the numerator here is a norm, operator norm of S on some L2 space, okay, squared. And Padashevsky and Sarnak showed that when n is equal to 1, so the group is SU2, okay, they showed that this norm has a lower bound is twice square root of size of S minus 1. It's just like the Alambopana lower bound. And if this set S is this special set SP that we choose to do the Ramanujan graph, and that has a norm which is a twice root T, which is the minimum possible. So that's the optimal one. And so when you have and this set SP has all the properties we want, and that's called the Golden Gate set. Okay. So in quantum computing, one of the goals is to find such kind of Golden Gate set. It turns out that number theory can be used to find this Golden Gate set. And the reason that it's good is because that it has Ramanujan conjecture holds some property behind it. So I just want to end to say that everything we talked about for GL2 over Q or 6/10 to group U3 is GO3 and marked out by the center of the Q by Ebra and the Pazashevsky. Okay. So so this group is compact at the real place. We can find the infinite family of the discrete subgroup such that as unramified primes come to 1 Mach 4 and the double coset gives you two-dimensional Ramanujan complexes. On the other half, the prime unramified primes P come to 3 Mach 4, you get a finite biregular bipartite Ramanujan graph. Okay. And infinity, they get a golden gate set. Okay. So this is the extension from PU2 to PGU3 over Q. So I stop here. Thank you very much.
I just have missed the punchline. Namely, how does the Ramanujan conjecture help you analyze the spectral property of the average operator on the graph? Is there a relation?
Yeah. Those constructed using number theory is that is in this slide. Is that you is that here. Your quotient, the functions on the vertices of quotient can be interpreted as some automorphic function of some group. So if you choose your group properly, then you can make sure that all the automorphic forms, the non-trivial automorphic forms you want over there, they are generic cuspidal automorphic forms. And so this is where Ramanujan conjecture comes in. So you have the Ramanujan property, and that Ramanujan property is precisely with the one which is used to define Ramanujan graphs or Ramanujan complexes. Okay, here. You see the Ramanujan property, so when n equals to 2, Ramanujan complex becomes Ramanujan graph. Okay, that's the same thing here. You have something called, maybe I should have said it. So Ramanujan complex means that this expression, or the non-trivial zeros, have the same eigenvalues. It's equivalent to saying that all the representations of group is say so since all the spherical representation, non-trivial spherical representation appears here, that is canted. So but you see that you hear this magic word, canted. So it's put together several cuspidal representations which satisfy Ramanujan conjecture. It is non-trivial. This is why I find it sort of intriguing that because the things are very unrelated, but then find a way to relate it.
有没有其他问题？如果没有的话，那我们再次谢谢李老师精彩的演讲。